Okay, so we discussed a little bit yesterday. I was very slow, and my plan is very ambitious, but I don't think I can cover all these things. But nevertheless, I wanted to have a slow start, and so that we can set the stage. So yesterday we reached up to this point where I could introduce the three-flavor neutrino oscillation framework in front of you, and most of you know most of the things about this, but let us see if we can add something to your knowledge. So we were talking about these three Euler rotations, what are their physical meaning, right? Now I want to start today with an emphasis on this third mixing angle theta 1,3. So this was the smallest lepton mixing angle that got discovered in 2012, right? The year Higgs was discovered by the modern reactor experiment called Diabe. And there are other two experiments, Doubleshow and Reno. They also contributed to this journey of theta 1,3. So now, if you see all these three mixing angles, this is one of the precise measured mixing angle in three-flavor framework. Okay. Now, I want to highlight that what is the importance of this theta 1,3 discovery in 2012. It is just 10 years back it happened, right? Now, I explained to you yesterday that if this theta 1,3 would have been 0, then the possibility of seeing CP violation or measuring the value of CP phase will not be there, right? All of you agree with me? All of you, right? So now with the discovery of theta 1,3, we made sure that we are in three-flavor regime. And that immediately gives you an opportunity that, okay, let's try to explore this CP phase, delta CP, correct? Another important thing that theta 1,3 brought into the picture is Earth's matter effect. And I will try, if we can discuss on that. That is one of the topics. So if this theta 1,3 would have been 0, then try to appreciate that there will be no nu mu to nu e transition or nu e to nu mu transition in long baseline experiment. All these long baseline experiments like T2K Nova, which are taking data now, you must have heard about these experiments. There are upcoming experiments, Dune, T2 hyper K. They are all trying to look for nu mu oscillating to nu e in their detector, right? But at atmospheric mass scale. Now, this transition will not happen if theta 1,3 would have been 0. So, finite theta 1,3 makes it possible that nu mu oscillates to nu e. It will be very clear when I will show you the probability expression. So if this theta 1,3 would have been 0, all these experimental program, T2K, Nova, Dune, T2 hyper K, this is a major chunk of the future neutrino physics. They will not be there. Because theta 1,3 is non-zero, so they can see nu mu oscillates to nu e at the atmospheric mass scale, not at the solar scale. Correct? So I should say that this discovery came at the right time so that we people could imagine how the neutrino physics will evolve in the next coming 2 to 3 decades. Clear? Another thing, the issue of neutrino mass ordering, I will come to that, for which you need Earth's matter effect in terrestrial experiment. If this theta 1,3 would have been 0, there is no way you can feel Earth's matter effect. That means there is no way you can discriminate between normal ordering and inverted ordering in long baseline or atmospheric neutrino experiment. So this mixing angle plays a very important role. I would ask all of you, if you have time, just think about theta 1,3 is non-zero, so what? Ask this question, write it down. And just think about it, write down the points that what would happen if you assume that this theta 1,3 is 0, what would happen to your three-flavor paradigm? What are the problems you will face Are there any alternatives to fix those problems? If theta 1, 3 would have been 0? We are phenomenologists, so your imagination can go anywhere. So think about this. Okay, so to wrap up the 3-flavor framework, we have these 6 independent parameters: 3 mixing angle, 1 CP phase, 2 independent mass splittings. Now, let's stare a bit on this UPMNS matrix. This is the unitary mixing matrix. And I told you these are the elements that governs the oscillation, right? Now, this is U mu 3. That means this component tells you basically that how much nu mu component you have in the nu 3 mass eigenstate. And this U tau 3 tells you how much nu tau component you have in the nu 3 mass eigenstates. And in nature, these are the fixed quantity. How you parameterize them, it's up to you. So these are the best fit values with some error that we have on these 3 mixing angles and on the CP phase. Just look at the numbers. So these mixing angles are quite large, right, as compared to the CKM mixing that Rukmani was talking about yesterday. And this is the CP phase. We have just started probing this CP phase. So I quote these numbers from a global fit studies where I did not consider the super K atmospheric neutrino data. And I assumed that this is the neutrinos are normally ordered. Now, I want to tell you, in the global fit picture, the most notorious data set is super Kamiokande. It is very difficult outside the collaboration to fit their data. If they provide some information, we just take it and use it. Because most of the time, we don't have information which are publicly available. So people sometimes give you global fit after fitting all the data, what are the measured parameters with and without super K data. If you trust their analysis with atmospheric data, you take these values. If you don't trust them, they also give you the values without super Kamiokande data. But super K data is very, very important now. If you want to measure neutrino mass ordering, if you want to measure also theta 1, 3, if you want to see Earth's matter effect, if you want to resolve the neutrino mass ordering issues, super K is doing a fantastic job. If I get time, I will elaborate on that. So this is without super K, you have this fit. I will just give an example. If I use super K data, that these 2 parameters, the theta 2, 3 and delta CP will be affected much. If I use super K data, this theta 2, 3 from 49 will go to 42 or 41. Just if I use super K data in my fit, this value from higher octane, it will flip to lower octane. I'm just giving an idea. And this CP phase, which is around 200 degree, will move towards 230 degree or so. So you see how important the super K data, whether you consider it or not, and whether you really consider it in a right way or not. Correct? So this is the elements of the U matrix, and you can see these are the 3 sigma ranges. So you should appreciate that these ranges are quite large. First, why I am showing you these numbers? So just stare at them. These ranges are quite large, and these are 3 sigma ranges. And another thing you should observe, that the off-diagonal elements are also not very small. They are quite large. You can see the off-diagonal elements. That tells you that neutrinos loves to mix. The mixing angles are large. If the mixing would have been small, what would happen to this matrix? Tell me. If the mixing angles are small, what would happen to this matrix? Yeah, this will all become like a diagonal, right? The off-diagonal elements will be close to 0. This is the case we have for the quark mixing. That is the place where this PMNS matrix differs from CKM matrix. Neutrinos love to mix. So here, just some facts that in the CKM matrix, the mixing angles are around 13 degree, 2.4 degree, and the smallest one is 0.2 degree. Now you can compare these numbers with these numbers, and you are convinced that neutrino mixings are indeed large. And it has a far-reaching consequence when you do phenomenology. Okay? Another thing, when we want to build neutrino mass model, one of the well-discussed pattern was the tri-bimaximal mixing pattern, which tells you that this sine of theta 1, 2 around 1 by root 3 and sine of theta 2, 3 is around 1 by root 2 and sine of theta 1, 3 is 0 and delta is undefined there. This is the tri-bimaximal mixing pattern. So you can see here that there is a slight departure if theta 1, 2 is around 35.3 degree, but our measured value is around 33 degree. There is a departure. If TBM is correct, then theta 2, 3 has to be maximal. But now there are hints that they are non-maximal. It can lie in the lower octant or in the higher octant. Correct? But the major thing is theta 1, 3. The tri-bimaximal mixing pattern suggests that theta 1, 3 should be 0. And here we have a big departure because the measured value is around 8.5 degree with very high precision. So these are the take-home message that I was telling yesterday. If you can measure these parameters very precisely, you can rule out various predictions. Okay, and this was one of the predictions. So this TBM pattern is now ruled out at more than 5 sigma confidence level, the 0th level TBM pattern. Okay. So now I will briefly tell you the open questions. You must have heard about this. So if I take the present data that are available to us, and if you want to arrange the neutrino masses, then from the solar neutrino data, it has been established that M2 is heavier than M1. And what is their gap? A value of delta M square to 1. Correct? So this splitting, how you will arrange them, it is fixed. It is known that M2 should be heavier than M1, and their gap is also well measured. Now the question comes, the third mass eigenstate. Now present data, modulo some hints, allows you to place this third mass eigenstate on the top of M2, which we call the normally ordered pattern. If you don't like it, you can also go in this way, where you can make this mass eigenstates heavy and you put this M3 mass eigenstate below M1. And this is called inverted ordering. Make it very clear, I am going very slow. Okay. So from the present data, we know again the gap, but we don't know the order. Clear? Whether neutrino prefers this picture or this picture, this is an open question in neutrino oscillation physics. Number one. Okay? And how to resolve that? I told you. We are lucky that theta 1, 3 is non-zero and it is not that small, like few degree. It is almost close to 10 degree. And let us try to appreciate during my lecture that non-zero value, how it gives you an handle to resolve this question in long baseline experiment or atmospheric neutrino experiment. So target is very clear. Okay? So here, now from this picture, you can immediately see that we only have a lower bound on the mass of the heaviest neutrino, because if you assume that my M1 is say 0, then you can calculate what is the value of M3, lower bound on the heaviest mass eigenstate, which is around 0.05 electron volt. Neutrino oscillation is sensitive to atmospheric mass square difference, not the absolute mass scale, right? You have seen in Andre's formula. In the neutrino oscillation probability expression, these masses are coming as a difference of their squared, right? Not the absolute mass. For that, we need to rely on some other experiments. So, but from this small exercise, you can get some idea about the lower bound on the heaviest neutrinos, which is also very small, 0.05 electron volt, right? This is clear? Now, I believe that this matter effect inside the sun was crucial to fix the ordering between M2 and M1. Inspired by that, we believe that the matter effect inside the earth will play an important role to fix the other ordering. Okay? There are other ways. Juno, which is going to start taking data next year, they don't rely on Earth's matter effect to resolve these issues. If I will have time, I will explain how they are planning to measure neutrino mass ordering. They don't rely on theta 1,3 or this Earth matter effect. They have a different way of measuring neutrino mass ordering. So there are two ways at present you can resolve mass ordering. In your terrestrial experiment, like in atmospheric and long baseline, you exploit theta 1,3 and the Earth's matter effect, and you can distinguish between these two pictures. But in Juno, which is a medium baseline reactor anti-neutrino experiment, they try to distinguish between delta m square 3.1 and 3.2. There is a subtle difference between delta m square 3.1 and 3.2 value, depending on whether neutrinos are normally ordered or they are ordered in an inverted way. Because if neutrinos are normally ordered, the largest mass splitting is delta m square 3.1, right? M3 square minus M1 square. But if neutrinos are ordered in this way, then what is the largest mass splitting? It is delta m square 3.2. And they have some small difference because of the solar splitting, right? In one case, it gets added up. In one case, it gets subtracted. So Juno exploits that. And for that, they need very high energy resolution, very precise energy resolution. But that's a different story. Another thing I want to mention, that when we ask this question about neutrino mass ordering, so think about this. So we are talking about delta m square 3.1. Okay, so you have axis like that. This is 0, and I'm talking about delta m 3.1 square. Now, I know from the present base speed that I lie somewhere around here, 2.5 10 to the power minus 3 eV square with some error bar. Okay, you understand? So I'm allowed to move in this region with this base fit. Clear? Can you see this? Or if I prefer this side, I have a base fit here and I am allowed to move in this region. But these values are already ruled out by the data. Can you see? All of you can see? So the question is whether I lie here, this is normal ordering. This is positive, right? Delta m 3.1 square is positive. Or it lies, I stand here, which is delta m 3.1 square is negative, right? Correct? These values are not synonymous. Little bit difference will be there when you go, because delta m square 2.1 is getting added and subtracted, right? But you see, when you analyze your data set and you want to ask the question that I have the data, now I will fit my data once with this picture, once with this picture. And your data will prefer one of them, right? If your data is good. So this is called, you are testing a discrete hypothesis. Because it is like a binary question, yes or no. So when you want to test this picture to this picture, there is no smooth transition is there. You need to hop, right? Because these intermediate values are already ruled out. So that's why we say that when you want to explore neutrino mass ordering, this is a binary yes or no type question. That means you have a discrete parameter space which are allowed and you are testing between them. And when you want to analyze your data to say, okay, I am sensitive to neutrino mass ordering with this much confidence, you have to adopt different numerical techniques to code the sensitivity as compared to suppose you want to measure theta 2, 3. So theta 2, 3, here you have 40 degree, here you have 50 degree, and this is the 3 sigma range. So any value is allowed within this range, right? So you don't need to hop from like 48 to 44 because any value is allowed in this range. So when you want to measure theta 2, 3, this parameter is continuous. There is no discreteness is there, right? They have a boundary, but there is no discreteness over there. So you can use Will's theorem here. But when you ask this type of question, that you can't use Will's theorem. And you should pay attention to Adam's lectures, and it will be very clear to you. So, and you should also study yourself. Why, when you have some discrete measurements, you can't use Will's theorem? Very important. In your course of study, you will do many analyses which are discrete in nature. So then what kind of analysis you should do to code the sensitivity of your experiment? So if your hypothesis is discrete, Will's theorem is not applicable. Okay, I'm just giving you hints because I can't go in detail, but then you start thinking about that. Okay, clear, fine, let's move. Another issue is this theta 2, 3. So if I see the present data, there are hints that this sine square 2 theta 2, 3. So focus on this quantity. That it is not exactly equal to 1. So in super Kamiokande, they see the disappearance of nu mu to nu mu, right? You have in atmosphere nu mu, half of them are oscillating to nu tau and they are measuring how many nu mu's are survived, correct? Now at the leading order, their survival probability looks like that. You have two pieces, sine square 2 theta 2, 3, sine square 1.27 delta m square 31 L by U. You must have seen that. This is in EV square. And if you prefer, this L is in kilometer and this E is in GeV, correct? In natural units. Okay. This is a conversion and then this 1.27 comes when you convert from natural units to your practical units, correct? Now if theta 2, 3 is 45 degree, then this is 1, right? And if this is also 1, then what would happen? P nu mu to nu mu is what? 0. That means full oscillation. All of the nu mu's have oscillated to nu tau. So if you fit the super K data in two flavor scenario, okay, and in two flavor, forget about the matter effect, the leading term looks like that. You have only two simple sine square function. So the data is now hinting, and also MINOS, there are long baseline experiment called MINOS, okay. So if you feed mostly MINOS and super K, so there are some hint that this quantity is not exactly 1. Sine square 2 theta. That means theta 2, 3 is not 45 degree. Now suppose you measure this quantity and you find out this is 0.98. Suppose. then you can immediately see you will get two values of theta 2, 3. You see, if your sine square 2 theta 2, 3 is close to 1 but not exactly 1, you will get two values of sine square theta 2, 3, right? One value will be below 45, another will be above 45. You all appreciate this, right? Correct? So you can just do it yourself right now, that if it is 0.9, what are the two theta 2, 3 solutions you get? Just do it right away. Okay, while I am talking to you. You can just do it, or 0.9, take any value. You will see that you will get two solutions. So the solution that is below 45, we call it lower octane solution. And the solution that you get at above 45, we call it higher octane solution. So if lower octane solution is, say, 42 degree, then the higher octane will be 48, right? Because sum has to be 90. Correct? So that is, we call the octant ambiguity of theta 2, 3. At present, I must say theta 2, 3 oscillates. Every now and then, 3 months, 6 months, when we have new results and we fit, it goes to lower octane to higher octane. So it depends on which data set you are using, who is fitting the data, when you are fitting the data. So this value of theta 2, 3 is very unstable. That's why I call it the oscillate, between 40 degree to 50 degree. That is the rough picture. They can be anywhere. I don't have a preferred value. I know their ranges, but they can be anywhere. So when you think about theta 2, 3, the question is, what are the questions you can think of? First, you do your experiment. You try to measure its value. Okay? Now, if you see that your sine square 2 theta 2, 3 is not 1, but it is slightly deviated from 1, then you will get two solutions. Then your job will be, okay, in nature, there will be only one solution which is valid or true. So I need to discard the opposite solution, right? That is the theta 2, 3 octane problem. We can resolve it in long baseline experiment, also up to some extent in atmospheric Newtonian experiment also. So this is an open question. First, you need to convince yourself that theta 2, 3 is deviated from maximal mixing. So the first phenomenology that you do is called deviation from maximal mixing. First thing, you can do phenomenology, you can write papers. You want to ask the question, I have the data, at what confidence level I discard 45 degree solution? In literature, it is known as deviation from maximal mixing. Once you are convinced that, okay, I am deviated, immediately the question will come, okay, you are deviated, but in which octant? Because your data can give you two solutions, 42, 48, 43, 47, 44, 46. So once you nail down this question, the next question comes, octant of theta 2, 3. Then you want to ask the question, okay, I am deviated from maximal mixing. Now let me fix the octant. Correct? Clear? Once you fix the octant, so in your parameter space, say this is delta m square, this is sine square theta 2, 3, suppose. You get two solutions. One of them is fake, one of them is true. Correct? So once you know that, okay, this is my right solution, then the question comes, let me try to measure it more accurately so that I can reduce the allowed parameter space. This is called precision. So the third question is, then comes precision in theta 2, 3. They are connected little bit, but I always think this should be the pattern. This should be the sequence. Any questions? Any questions? Clear? So this is the phenomenology of theta 2, 3. We are actively working on that. You are most welcome to work on that. Some of you are also working on that. Yes. Yeah, that is the result at some confidence level, yes. Yeah, it is 1 sigma. If you take 3 sigma, still you can think like, if you go 3 sigma, then you can cross 45 degree. It is 1 sigma number. But I told you, if you take super K data, the feed goes to opposite octane, right? 42 degree. You can't ignore super K. Here, this is without super K. That means your data is not stable to answer this question. It fluctuates, right? So that's why I'm telling you, know the range, lower and higher range. But which octet it belongs, whether it is really deviated from 45 degree, these are open questions. Hmm. Correct. Correct. Yeah. So in nature, this deviation can be 0.0001 degree. I don't have any handle. But then I will not be able to resolve this in next 20, 30 years. But if it is above 1 degree, there is a hope. That is the punchline. Okay? If Dune comes, takes data for say 10 years, we have done the simulation, then if it is 1 degree, 1.5 degree, there is a chance that at 1 sigma, 2 sigma, you should be able to distinguish. Beyond that, there is no hope. So, this is the phenomenology of theta 2, 3. Yes. Very good question. So, all these information come from one oscillation channel or 2 oscillation channel. So, allow me to go. So, there are so many unknowns, but you have few equations. So, there will be degeneracies, right? If you have 3 unknowns, you need at least 3 equations to solve them. But you have many questions, CP, theta 2, 3, mass ordering and blah, blah, blah. But you have only few equations. So, there will be degeneracy. So, when you say, this is my measured value of theta 2, 3, you also need to worry, what was your mass ordering? What was your CP? So they are connected because you get the information, okay, from the same plate. Okay, makes sense? Let's proceed. So I want to highlight that when I say theta 2, 3, octant, what is the physical meaning? I mostly ask this in interviews, but I hardly get the answer. So here is the answer, okay? So if theta 2, 3 is below 45, the question that you are asking, that again, how much nu mu and nu tau is there in the nu e component, in this nu 3 component. I'm talking about this for last 2 days, right? So you can convince, if you look at the UPMNS matrix, the 2, 3 and 3, 3 element, because ratio of that gives you theta 2, 3, right? I told you yesterday. So if theta 2, 3 is lower than 45, then in this nu 3 mass eigenstate, nu tau has more shear than nu mu. And if it is in higher octant, then nu mu has more shear than nu tau. And this blue shear, the shear of theta 1, 3 is almost fixed. Theta 1, 3 value is fixed, right? Correct? So this is the physical question you are asking. When you build the nu 3 mass eigenstate, which one takes more shear? Nu mu or nu tau? That is the issue of octant. Clear? That is the physical meaning of octant issue. The last issue, whether CP phase, it is violated in the neutrino sector like in the quark sector. There was some discussion yesterday. So mixing can cause CP violation. I convinced you. We are in 3 flavor. And in UPMNS, you can invoke one CP phase, Dirac CP phase. But you can see this CP violation provided these are not 0 or pi, because these are the CP conserving solutions. Okay? Now, in literature, the way we quantify it, we define a quantity called CP odd asymmetries. You should all estimate it, as a homework. In vacuum, try to estimate this delta P alpha beta. Take alpha beta any flavor. Please do this exercise because I have given you the 3 flavor vacuum expression. There was a real part, there was an imaginary part, and then try to calculate that. What is this? This is the difference in the probability of neutrino minus anti-neutrino. Now, this CP odd asymmetry will be finite when you see the appearance of a new flavor. Look at carefully. I am not writing alpha equal to beta. So this tells you that if you want to probe CP odd asymmetries, you need to rely on appearance channel. And the best bet is your long baseline experiment because you produce new mu beam and you are looking for nu E in your detector, the electrons. Correct? So that's why long baseline experiments are one of the favorite bet to probe the CP odd asymmetries. And once you will do this homework, you can write down this CP odd asymmetry in this nice fashion where this JCP is the famous Yarlskog CP odd invariant, where you see all the sign of all the mixing angles comes. If any of the mixing angles are 0, then it vanishes, right? If any of the mixing angles are 0 or delta CP is 0, Yarlskog CP odd invariant vanishes. Yes, Shailesh, tell me. Yes.
And we have measurements of theta 1 and theta 1 2 as well. So can we infer that, okay, this is the theta 2 octant as well using this Yarlskog?
See, this Yarlskog invariant is a part of your oscillation probability, the asymmetry. So definitely, when you have other parameters in control and if you fit the data, you are saying my theta 1 2, theta 1 3, delta CP all are under control, you know the hierarchy, then definitely you are very close to theta 2 3. Okay. Either you look at in this way or you just fit the whole data, doesn't matter, you will get that information. So that's why I say 3 flavor effects, that is the topic of my discussion, are the key for CP violation. If any of the mixing angles are 0, this is 0, right? That means you don't see CP odd asymmetry. Convinced? Another thing. You have seen these 3 orderings, right? So it tells you that we are in 3 flavor. If I go to 2 flavor, what would happen? The gap between any of the splitting will merge, right? So any of the splitting will be 0. Correct? That is also 2 flavor. Let's go there. You see this part. If your delta M21 square is 0, then your delta M square 32 and 31, they are same, right? 31 and 32 are then same because 21 is 0. Correct? And here you have 32 and 13. So delta M square 13 square is minus of delta M square 31 square. And this is sine, not sine square. Please go with me. So this will be minus of sine delta M square 31 2 by E 2E into L. And this is delta M square 32. And there will be a minus sign here, right? Because this is 0. And that means this part is 0 and your CP odd asymmetry is 0. So whether you make one of the mixing angles 0 or you switch off one of the splitting, you are in 2 flavor. Clear? Clear? Okay. So the conditions for observing CP violation, we need non-degenerate masses. That you are convinced. Only neutrino mass is not sufficient. We need the splitting, the difference. If you have 2 flavor, M1 can be 0, but M2 is finite, I am fine. I have the difference. So masses should be non-degenerate. Mixing angles should not be 0 or pi by 2, right? You can convince yourself. If it is pi by 2, then also life is difficult, right? The sine 2 theta and delta CP should not be 0 and pi, and we have satisfied these 3 conditions almost. So we are in a good regime, good shape. Okay, so this has been discussed yesterday. This is the VCKM, the CKM mixing matrix with 1 sigma error, and this is UPMNS with 3 sigma error. And we have a hell lot of work we have to do so that we can take this matrix to a precision of CKM. If you stare at these numbers, right, the error bars are way large here compared to this. Correct? But the good thing is, our mixings are large. So if you calculate the JCP, this turns out to be around 10 to the power minus 2 for PMNS, but for CKM it is 10 to the power minus 5. So there is a 3 orders of higher this JCP is for PMNS. So you have more chances to see CP odd asymmetries in neutrino oscillation. So very quickly, when we think about CP violation, because from Sakharov's condition, this is one of the conditions by Sakharov, right, that you need C or CP violation. You should see more events, more phenomena which are violating CP symmetry, right? One of the conditions by Sakharov. So if you see the neutrino standard model, there are 5 irreducible CP violating phases. Let's count them. We have talked about the CKM phase, right, which is around 70 degrees. And so far, this is the phase which governs all the CP violating phenomena. In principle, you can have a CP phase in your strong interaction, and with the development of QCD, so this is called the strong CP problem, and there the CP phase of the theta of the QCD vacuum, it is very, very small at present. It is less than 10 to the power minus 10. Okay. So in the lepton sector, we have this Dirac CP odd phase delta CP that we talked about in the PMNS matrix, and we can measure them in neutrino oscillation experiment. But if neutrinos are Majorana particle, then nu equal to nu c. So you can't redefine their fields. So there will be 2 more phases. But in oscillation, they will be rotated out, correct? So you will not be able to measure these 2 extra Majorana phases in oscillation experiment, and you have to rely on lepton number violating processes. At present, we don't know their values, but there is a way to measure them if they exist. Okay, so I can tell you if I have time, but just bear with me that this CKM CP phase is not responsible for the observed baryon asymmetry. If you just rely on CP symmetry violation, then this PMNS CP phase is the only hope. And if you measure this CP phase to be non-zero in the coming days, then definitely it will shed light. There will be a strong indication. I must not say that it will be a proof that leptogenesis is the origin for the cause for the baryon asymmetry, but there will be a strong indication towards that. There is a huge literature, I don't have time, but to measure the CP phase, which is my job, we need 3 flavor effects. So, are you convinced now before I proceed? To measure CP, we need to be in 3 flavor. We need to measure the 3 flavor effects. How? I told you all the open questions. One of the mostly discussed channel to discuss these unsolved issues is nu mu to nu e oscillation channel. You must have seen this slide many, many times. What we have done here, so stare it, I wait for 10 seconds. Take a look at this formula. Because I can spend 2 hours only on this slide. Everything is there. If you take this slide, go there and come here, you will find one problem. Believe me. So just stare it at this and then I will start explaining. So what is this? Here we have written the appearance probability. Remember, CP odd asymmetries are visible when you have appearance channel. I wrote alpha not equal to beta. Remember 2 slides back? You need to rely on appearance. In disappearance, you have electron disappearance. I told you CP phase will not appear there. In case of muon, survival in atmospheric, you will only have cos delta CP term, which are very, very suppressed. There will be no sin delta CP term because it's a survival channel. So there will be no CP violating term in those expressions. So take home message, when you measure disappearance or survival of neutrinos, you can't measure CP violation. In nu e to nu e, you are blind to CP. In nu mu to nu mu, you have only cos delta CP term at a very subleading level. So the best bet is to look for nu mu to nu e appearance. This is the job of all the long baseline experiment, correct? You are learning about the beams, right? So if you expand, because this formula is very complicated when you take 3 flavor and you have also earth matter effect. So if you expand this formula in these 2 parameter, alpha is the ratio of 2 splitting, and this is a small quantity, right? This is 1 by 30. So 0.03, alpha is 0.03. Agree? And this theta 13 is also very small, around 8.5 degrees. So sine 2 theta 13 is around 0.3 also. Agree? So these are small quantities. So if you expand this probability in these 2 parameters up to second order, you can write down these 4 terms very nicely. So let's go piece by piece. Okay? Go with me, please. So the first term, you have sine square 2 theta 13. Then you have sine square theta 23. And then you have some term here. This delta is the oscillation phase, delta m square L by 4E. You are familiar. And first time I am bringing this term called A hat. What is A hat? A hat is the ratio of the Wolfenstein matter term. This is the MSW term, right? You have learned in Andre's lectures. This is positive for neutrino, negative for antineutrino, right? Homework problem. Derive it. It will take some time if you don't know how to derive this. And you are writing all these papers. Derive it that this Wolfenstein matter term is positive for neutrino and negative for antineutrino. Please, all of you should derive that. Doesn't matter whether you are working for experiment, theory, phenomenology. Basic standard model calculation. Derive it that this Wolfenstein matter term should be, first derive this term and then derive what is happening if you switch from neutrino to antineutrino. Okay, please do that. So this A hat is the ratio of this Wolfenstein matter term, and you see this is also in EV square unit, right? This is EV, energy is also EV. This is EV square divided by delta m square 31, which is EV square. So this is a dimensionless quantity, correct? So matter effect is coming into the picture through A hat. Agree? So here I told you that if theta 13 would have been 0, that was the first statement I made today, there will be no nu mu to nu e transition in long baseline experiments. Convince yourself. I am standing. Convince yourself. If theta 13 would have been 0, this is gone, this is gone, this is gone. And what is this term? Homework problem. Take theta 13 tends to 0 and what happens to this formula? Just do it yourself. You have the slides? Do it at home. This is the standard solar term. You will see if you do little bit of calculation, you will see this is sine square of 2 theta 12 and this is basically the sine square delta m square 21 L by E and this is the cos square theta 23. Okay, so this is the solar term. So there is no theta 13 dividend nu mu to nu e appearance will happen. So if theta 13 would have been 0 in 2012, there will be no long baseline program. Imagine the consequence of theta, large theta 13. Non-zero theta 13. If theta 13 would have been 0, there is hardly any physics you can do with T2K, nova, d und T2 hyper K. All these terms are 0. And you land up with the standard solar term. So do this calculation. Take theta 13 is 0 and see, and then you try to expand and see whether you get back the standard solar term or not. Okay? Let's come to theta 23. So here, theta 23 is coupled with theta 13. So when you measure this mix probability, you can't disentangle between theta 13 and theta 3. Somebody asked me just now. So if you know theta 13 from reactor experiment, that I know theta 13 very well. So the error on these blue terms are very small. And if you measure the product of these two, then you can infer about sine square theta 23. Correct? Now you appreciate the leading, this is the leading term. If you are learning globes, so, and you are familiar with this expression, can you do a C++, write a C++ code in these few days? Just write it. Believe me, it will take only 2 hours. You write a C++ code, T1, T2, T3, T4, and just plot it as a function of energy, or calculate with the best fit values of oscillation parameter, what is the typical strength of this term. No matter how much I shout, if you don't do it by your hand, you will not appreciate. Okay, so please do that. I'm not telling you big things, you should be able to do that. So if you do that, this is the leading term. But here, if you know theta 13 very well, then you can infer about this term, right? Sine square theta 23. And this is sine square theta 23. So you are sensitive to octant. It is not sine square 2 theta 23. Clear? The leading term in this channel is sine square theta 23. It is not 2 here, like the disappearance channel. I wrote somewhere. Here it was sine square 2 theta 23. So you are blind to octant. Here you are not blind to octant. You can measure the octant because octant means sine square theta 23 either 0.4 or 0.6, right? 0.42 or 0.58 or something, 48. So you are convinced that this channel gives you octant also? Yes or no? The leading term contains sine square theta 23. This theta 13 is fixed by reactor. Now comes the delta Cp. You see, in the second term, we have the sine delta Cp term. This is called the Cp odd term, and you have the Cp even term. So I was telling you, if you rely heavily on this channel, then there are so many unknowns. Suppose you don't have information from other experiments. Just think about it. So if you want to measure everything from this one channel, theta 13, theta 23, delta Cp, then this delta m square 31, its sign, and then the sign of this quantity, then there are so many unknowns you are asking from one equation, right? So what would happen? There will be degeneracies. You will always get many combination of x and y to satisfy the same equation, correct? This is called the so-called degeneracy, issue of degeneracy in three-flavor paradigm. So the job that we have in hand, let me tell you, summarize. In three-flavor phenomenology, every day we wake up and think, how can I resolve these degeneracies? There are many ways you can tackle this problem. One of the important ways is you do experiments at different L by E. You think about T2K, 295 kilometer, off-axis experiment. NOVA, 810 kilometer. That is also off-axis experiment. You can ask me why they are important. Because they bring information at different L by E. Agree? Because they are oscillation is a L by E phenomenon, L by E driven phenomenon. So you have information at different L by E. T2K free from matter effect. When you travel 800 kilometer in NOVA, you have matter effect. So there is a complementarity. You can see already in T2K and NOVA. These are the two long baseline experiments taking data now. So one of the ways to resolve these degeneracies, you do experiments at different L by E. Another way, you probe different channel. Like I told you, in reactor, the channel you probe is nu E bar to nu E bar, right? Disappearance of electron antineutrino. It will give you a delta Cp theta 23 free measurement of theta 13. Because this channel, the formula that is relevant for Diabe is 1 minus sine square of 2 theta 13 sine square delta m square 3 1 square L by 4E. So you see nothing is coming in the leading term, only sine square 2 theta 13. There is no delta Cp, there is no theta 23. So from reactor you measure theta 13, plug in here. So you remove the theta 13 delta Cp degeneracy and other degeneracies related to theta 13. So that is done. We have resolved that degeneracy with theta 13. But we have other degeneracies. What is that? You see, you don't know the sign of delta m square 31, right? I just told you this is the neutrino mass ordering problem. So depending on which sign you have in nature, this A hat will take different values, right? So this tells you that, but if this matter effect is 0, then this A hat is 0, right? Just go with me. If matter effect is 0, this term is 0. And if A hat is 0, you are not sensitive to the issue whether this is positive or negative because it is gone. That's why in the beginning I told you, matter effect is the key to resolve the mass ordering problem. If this term, the numerator is finite, Doesn't matter whether it is neutrino or antineutrino. If it is finite, then you are sensitive to the sign of this quantity. That is the ordering issue, right? Neutrino mass ordering issue. We are not doing, big things, but they're small things, but try to appreciate. You all agree that how through matter effect A hat can give you information on this delta m square 3 1? Agree? So this changes sign, this quantity, whether the neutrinos are normally ordered or they are ordered in an inverted fashion, key to resolve hierarchy, but there is a downside of that. Since this term changes sign when you go from neutrino to antineutrino. If you work in vacuum, what is the only difference you have when you go from neutrino to antineutrino? Please answer. Neutrino to antineutrino, what is the major difference? Tell me. Delta Cp. Delta Cp goes to minus delta Cp. U goes to U star. And that causes difference between the rate of probability with which neutrinos and antineutrinos will oscillate. And that is the Cp odd asymmetry, right? The difference of these two. Life was very easy. You do measure neutrinos, their probability, measure antineutrinos, their probability, take the difference, life is easy. But then these neutrinos travel through matter, right? You always have some matter, whether it is 200, 300 kilometer or 800 or 1300 or 5000. You have some matter through which neutrinos are traveling, correct? So once you have matter alive, then you have to worry about this term. But think carefully. This term also changes sign when you go from neutrino to antineutrino, correct? So even if delta Cp is 0, you measure neutrino and antineutrino probability in matter, you can see some difference, right? This is called the issue of fake Cp asymmetry. Try to go with me, please. So matter effect helps you to resolve the neutrino mass ordering problem. I just convinced you. But at the same time, in this channel, it will give you fake Cp asymmetry. Because ultimately in the experiment, you measure the neutrino transition rate, antineutrino transition rate, take the difference. Now, if you see some difference, say, oh, okay, I have seen the difference, so delta Cp is non-zero. Wait, you have this term also, the matter effect term. It also changes sign when you go from neutrino to antineutrino. So the difference that you will see, the Cp odd asymmetry that you will measure in your experiment, will you attribute this to delta Cp? Or you will attribute this to this mass term, Wolfenstein matter term. Clear? That is a big problem. In the coming decade, that is a big problem that we need to address when you want to measure delta Cp. The Cp odd asymmetry because of the pure Cp phase. Matter will always become a hindrance. Matter will also give you asymmetry. That is called the fake Cp asymmetry. Delta Cp will give you the real Cp asymmetry. But in your measurement, they are coupled. How to decouple them is one of the biggest problems. That's why you do experiments like T2 hyper K in Japan, they have 295 kilometer baseline, right? So they will not be sensitive to matter because 300 kilometer, very less matter. So what they will give you, a genuine Cp asymmetry information. Agree with me? But when 1300 kilometer, the good thing is that they have a huge baseline, they will feel matter effect, so they will resolve neutrino mass ordering, and they will also measure the Cp phase there, but there will be some ambiguities. But when you add the data, T2 hyper K and dune, you resolve both the problem. That is the essence of three flavor phenomenology and the complementarity between dune and T2 hyper K. You ask in next few days always, why do we need to have two experiments at the same time? They are of same nature, but there are also complementarities. They bring complementary information. Did I convince you guys? Okay, I spent 10 minutes on one slide. Okay, so you are learning globes with Sushant. So try to plot these probabilities. I will not go in detail. These are the nu mu to nu e oscillation probabilities for different baseline. 295, then you have 810, 1300, 2300. The upper band is because of normal ordering, lower band is lower one is for inverted ordering, and the band is for the unknown delta CP. Can you see when I increase the baseline, that means matter effect, these two bands get separated? Means more at matter effect, you have more separation between normal and inverted ordering. Irrespective of the uncertainty in delta CP, because your delta CP can make this line uncertain by this amount or this amount, right? But you still have the gap. So this slide, you try to make these probabilities and you will appreciate. This is the octant problem. Here the lower band is for the lower octant solution of theta 2, 3. Upper band is for the higher octant. And you see there are some overlap because you don't know the delta CP. Again, the same expression. From this expression, you want to measure what is the octant of theta 2, 3, but delta CP say, oh, don't worry, I am there. You don't know me. So there will be degeneracies. And this is the degeneracy. If you plot it, then you appreciate it. Okay. So in atmospheric Neutrino experiment, so far I talked about nu mu to nu e, right? Appearance channel. But in atmospheric Neutrino experiment, you rely on disappearance channel, right? Mostly you have nu mu's from pion decay, and then you see how much they are oscillating to other flavor, correct? That is nu mu to nu mu disappearance channel. So let us take a look at that channel also. So here I have taken another approximation. This is called one mass scale dominance approximation. You will see a lot if you do oscillation phenomenology. It's called OMSD, one mass scale dominance approximation. What is that approximation? If delta m square 31 L by E is much larger than delta m square 21 L by E. So if you work with such L by E values, that this quantity is larger than this quantity, because you know delta m square 31 is 30 times larger than this, right? So if you work in this regime, then you can drop the terms which comes with solar frequency. You can drop this. So you are again going back to like two flavor, but you are dropping one frequency from the expression. Why? In actual calculation, you don't drop anything. You go to your laptop or computer and you do full numerical solution. But if you want to appreciate the underlying physics, you need analytical expression. That's why I showed you this analytical expression. You can see the physics over there, right? Similarly, this is also one of the analytical expressions for this channel, where I dropped this solar frequency. Correct? Just if you do that, you can write down the nu mu to nu mu survival in this nice compact form. Okay? Now appreciate here. Take theta 1, 3 equal to 0. Just take it, in front of me. Just see if theta 1, 3 is 0. Okay? Sit straight and do that. Just do, if take theta 1, 3 is 0, what would happen? I have written, if theta 1, 3 would have been 0, you will not be able to probe the sign of delta m square 31. Can you convince yourself? If theta 1, 3 is 0, then this is 0. If this is 0, then this term is gone. Correct? Here look at, if theta 1, 3 is 0, so this delta m square 31 in matter is nothing but delta m square 31 minus A. You agree with me? If this is theta 1, 3 is 0, this is gone, this is 1. So this is delta m square 31 minus A. Correct? Now if you plug that value there, this becomes 0, this becomes 0, right? Can you see? So if theta 1, 3 would have been 0, then you will not be sensitive to Earth's matter effect. Okay? And there will be no separation between normal and inverted mass order. So through this formula, in atmospheric neutrino experiments, you can be sensitive to sign of delta m square 3 1, whether it is positive, whether it is negative, right? It will make a difference here, right? If it is positive or negative, correct? But you can see there is no delta Cp here. Can you tell me why delta Cp didn't come? Even cos delta Cp is also not there. Because I have done the approximation, right? What approximation? Be loud. Yes, tell me. Yes, so I am again in two flavor. Great. So I will just spend last 5 minutes. This is the three flavor phenomenology. So I have taken this plot from this global fit paper. And sometimes we don't look at this plot. We just go ahead and we never pay attention. But in my lecture, you have to pay attention. So this is the global fit of all the data that you have from solar, from reactor, from accelerator, and from atmospheric. So look at this plot. In the x-axis, we have theta 2, 3. Sine square of theta 2, 3. That means you are sensitive to octant, not sine square 2 theta 2, 3, correct? And in the y-axis, we have theta 1, 3. Now you can see the interesting three flavor effect here because this fit is done without any approximation. You are in three flavor, no approximation. And you are fitting all the data. In the upper row, you have considered that neutrinos are normally ordered. You know what do you mean by normally ordered? M1, M2, M3. In the lower row, they have assumed that neutrinos are ordered in an inverted manner. M1, M2, and then M3 is below. In these two assumptions, they are fitting the data. In this panel, they have assumed the data from long baseline accelerator, solar, and Kamland. So no information from reactor in this panel. What are the three lines, by the way? One is at 1 sigma, another is 2 sigma, and the black one is 3 sigma, right? These are at what confidence level? What is the region allowed at different confidence level? And this dot is the best fit. That is the best fit from the global fit. Now see the magic. This is the shape of the contour. Seems like you have two solutions allowed, right? If you draw a line at 45 degree, then you have like kind of two solutions are allowed, right? One tail is going in the higher octant, one tail is going in the lower octant. Correct? And that is the allowed range, total allowed range. See the magic. Once I include the data from Diabe, mostly Diabe, short baseline reactor. By now you know what is the role of Diabe, right? What is the role of Diabe? Please tell me. Huh? They nailed theta 1, 3 down, right? So theta 1, 3 is measured, no uncertainty. You see what happened to this contour? The uncertainty in theta 1, 3 gets reduced from this. So that was the measured value by Diabe at 2 sigma. You see this straight line there? That was the only allowed value by Diabe. Diabe say, okay, I am nailing it down. Sorry. So you see from this contour you get there. This is the oscillation phenomenology. Where reactor with 1 kilometer baseline, and here you are dealing with 100 or 1000 kilometer baseline data. So this is the complementarity. Once you add the data, your allowed space goes down to almost negligible, right? You reduces a lot. You improve, right? Do you understand that this picture is better than this picture? First, let me ask you this. Do you understand that this picture is better than this? So adding more data helps. What helped you? The reactor. Now you see the magic of atmospheric. If you don't use super K and if you use super K. So up to this, you don't use super K. The moment you use super K, can you see? This contour flips to this. From higher octant, it goes to lower octant. So that's why I was telling you that whether you add super K data or not, your octant flips. You can see there. And the same story happens if you take inverted ordering. Let's go to another picture. That is even interesting. Here the correlation is between, it was theta 1, 3, theta 2, 3. Here now you see the correlation. I am going slow. Theta 2, 3 and delta m square. This is the atmospheric mass splitting. I will take 30 seconds, stare at them and see when you add again the data, how you improve in the parameter space and what are the differences happening. Just look at them. Again, when you add super K data, your octant flips, right? Here the preferred octant was higher octant, correct? Can you see the best fit, the dot? Where is the dot now? In the lower octant. So that is the ambiguity that super K data brings. We need more and more data because in nature there is only one preferred value, right? Our data is not strong enough to really measure it with higher confidence. That's why you are hopping here and there. And there is a tension between the data set. Okay? Now you go to the last piece, theta 2, 3, delta Cp. These are the two most unknown parameters in three flavor paradigm. Right? Delta Cp, almost unknown. We know some ranges, and theta 2, 3, I told you 40 to 50, anything is allowed. So now in this plane, correlation is even interesting. You see, this is the pattern you will get if you just rely on this data set. The moment you add reactor, now you see, you can ask me, why reactor? Reactor only brings information about theta 2, 3 and delta m square. Correct? Please go with me again. Theta 1, 3, reactor only gives you information about theta 1, 3 and delta m square 3, 1. Why they will make a difference when you see in the plane of delta Cp and theta 2, 3? Can anybody tell me? Tell me in a simpler language. So in three flavor, theta 1, 3 is there. And you need to integrate or marginalize over that unknown parameter space. And that will deteriorate these contours. It will make it big and hopping here and there. But if Diabe will tell you, no, I know theta 1, 3, you can't make me here and there. So then that will also affect this fit in delta Cp and theta 2, 3. You can see here. So even if you are not exploring your parameter space in theta 1, 3 plane, but it is playing its role in the three flavor picture. That is the three flavor phenomenology. Make sense? And this is when you add atmospheric data, again, this flipping is happening here also. You see, it was preferred here the lower octant, now it switched to higher octant. Correct? So that was my essence of three flavor phenomenology, which was my 50% task. This is the present status in solar sector. In 2018, there was some tension between solar and Camlan data. They were proposing different values of mass squared splitting of delta m square 2, 1. But lately, when Super K came up with their refined data, including the phase 4 solar data, and this new data from Super K is telling us that the day-night asymmetry is less. I am assuming that you are familiar with day-night asymmetry concept in solar Neutrino experiment. You are familiar with that? Because when you are taking data from sun, in the daytime, you see the neutrinos directly. But in the night time, these solar neutrinos are passing through the earth. So earth can play some role. That is called day-night asymmetry, right? So Super Kamiokande, in their solar neutrino sample, they have seen this asymmetry, day-night asymmetry. And recently, when they have refined their data set, they are saying that the asymmetry is slightly less, which helps to erase this tension. So this is the latest highlight from solar sector. And this is the final fit. I asked today 3 open questions. I will finish today with the present status. So this is the fit from all the data. And you can see that this blue line is with normal ordering and the red line is with inverted ordering. So you fit the data and you measure any quantity, delta Cp, splitting or mixing angle. Every time the preferred choice is normal ordering. You see, when it starts the bottom, that means that is more preferred, right? And the inverted ordering is excluded at this difference. This is the confidence level difference when you exclude the red line from the blue line. Blue line prefers the data most. That means normal ordering is preferred if you fit all the data, but the confidence level is around 2 to 2.5 sigma. So this can go anywhere. This can vanish, this can stay, this can grow. I can't tell you anything. Okay? What about theta 2, 3? If you see this theta 2, 3 fit here, there is a preference for lower octane. But I told you, if you change your assumption on data set, this can go to that side also. And delta Cp, this much we have the information that sine delta is less than 0. That means delta Cp cannot be or may not be in the upper half plane. Upper half plane between 0 to pi. So it should be in the lower half plane, which is minus pi to 0. So that's why sine delta is less than 0 at 90% confidence level. So this is the detailed slide. You can take a look if you want to do some phenomenology. And here I will stop. So this is the slide where you can see, okay, you are showing, because you love them, they are your friends. So you are showing all the results from this paper. They are from Bari, from Italy. But there are other groups are also doing global fit studies. Do they also tell you the same story? Because there are 3 groups. So here there is a nice comparison. So here what we have done, this is the latest till date what we have. So we have shown you what are the allowed ranges and best fit from 3 global fit studies. You can see this is by Esteban et al., which is the new fit. This is from Capozzi et al. That I just talked about, and this is by the Valencia group. So you can see, you take any parameter, the best fit values and the allowed ranges are more or less similar if you go with all these 3 global fit studies. And this is the relative 1 sigma precision in measuring this parameter. This tells you that global fit is very robust. You have so many data. Remember my first word yesterday. We have ample data from different sources, different L, different E, different systematics, but we have only one model, which is 3-flavor neutrino oscillation with matter effect. And it can fit almost 99% of the data in one framework satisfactorily. And it doesn't matter whether you do the fit or you do the fit, or he does the fit, or she does the fit. They all landed up in the same picture. It tells me that it is robust. Okay, so I will stop here. You keep staring at this slide. It will give you more confidence in neutrino oscillation. Thank you.
We have questions. Can you raise hands?
Questions? I still go slow, so you should have questions.
When you showed this Yal's curve invariant for the neutrino sector, you told it's 3 into 10 power minus 2. So what value of delta
Yeah,
Cp?
I will go there. Wait. Yeah, I'm sorry. I was a bit hurried over there. Yeah.
Yeah. What value of delta Cp for that you took?
Yeah, I took 90 degree.
Okay.
So you just put this is 1, and then you just plug these numbers, and you will get around 10 to the minus 2.
But delta Cp can be anything.
Anything, yes. So that will change this number. You have an error around that. But that is the maximum that you can think of.
Okay. Yeah. Okay.
Maximal Cp violation.
Thank you.
More questions? If you don't have question, I will assume you will do all the homework.
I have one from Sushant.
Yeah, clarification. Yes, Sushant.
You said that the solar neutrino data manages to fix the hierarchy between 1 and 2. That is under the assumption that of theta 1, 2. Theta 1, 2, if it is less than 45 degrees, then because it's a combination cosine 2 theta 1, 2 times delta square 2, 1. So if you assume that is less than 45, then it fixes the
and
hierarchy.
once you add Kamland, then everything gets resolved. The LMA solution.
Land allows theta 1 to greater than 40.
But the
But
tension,
the matter effect,
the energy dependence.
not from Camland.
No, from sun. The energy dependence for the high energy neutrinos, the upturn was very important to fix the M2 and M1 difference, the splitting in sun. The energy dependence of the solar neutrinos for higher energy neutrinos was very crucial.
Okay, any other questions? Okay, if not, let's thank Sanjib again.